our calculators, because we need this for today's lesson. Okay, if you want, you can borrow this one. I just realised Karen's is yeah, so you can use that. In case you need to try anything out.
It's like basically does.
Oh, is it? Oh.
Yep.
I better swap it over. Okay, so standard deviation and variance. We started this last lesson, so let's just read over some of the notes we took already. Okay, so standard deviation and variance. In our course, do we tend to deal more with the standard deviation for a population or for a sample? It's a population, good guess. So the standard deviation for the big group. So try to visualize this thing. It's the standard deviation for a population that we deal with more in our course. As Lauren keeps informing us, the sample is a random selection from the population. The symbol we use for the mean of a population is mu, and for mean of a sample we go X with a little line on it in terms of these formulas. So your GDC gives you two different standard deviations. It gives you the population one, which is the sigma, and it gives you the sample one, which is the S. But when we're asked just generally to find a standard deviation and they don't tell you to find the sample one, we assume we need to find the population standard deviation, which can be found on the GDC. You go stat edit, enter your data into L1 if it's just a single data list. If it's a frequency table, put your X into L1 and your frequencies into L2. Then stat calc one var stats, because you're just dealing with one list of variables. Because the frequency is not a separate variable, it's just relates to the first set of variables. One var stats, your X list should say L1, if your data's in L1, that is. If not, you enter that by pressing second one. And if it's a frequency table, you need to tell them the frequency is L2. We were just talking about how the calculator uses this formula. I don't know why there's a big line there. So the calculator uses this formula to do it for you. So this population is the square root of the sum of all the numbers minus their mean. So if, let's say for example, if the mean was 5, so say for example, the mean was 5, and the data set was, let's see, make sure I make one a little bit of mean of 5, 6, 4, 3, to get a mean of 5. But out of interest, to get a mean of 5, what should my last number be? Yeah, to get a 7. 7, yeah, how did you get 7?
Because it's 4 numbers, and then 5 times 4 is 20.
Good, yeah. So if there's 4 numbers, and we want a mean of 5, then they need to add up to 20. That's how, and we need to add up to 13, so we needed to have a 7. So let's say the mean was 5. If you were to work out the standard deviation by hand, using this formula, just showing you how you would do it by hand, you'd need to do 6 minus 5, work out all of these. So do this bracket part first. So x minus mu, for example, x minus mu, what would that be? 6 minus 5 would get you 1. 4 minus the mean, see we're doing each number minus the mean to start with. Minus the mean would get you negative 1. 3 minus the mean, negative 2. 7 minus the mean, 2. And then the next thing I would do is I would square all those answers. So x, oops, it's not x, that's x minus mu squared. So what's this one squared? 1. 1, yeah. But this one squared? 1. Good. But this one squared? 4. Good. And this one squared? 4. So see all the negatives become positive when you square them. And see how it's got the sum going on, the big sum symbol? And now just means add them all up. So what does 1 plus 1 plus 4 plus 4 equal? 10. Good. So we've worked out the numerator in that fraction. What are we supposed to divide it by?
4.
Yeah, 4. Why 4?
Because that's the number of numbers in the set.
Exactly, yeah, that's what n is. How many numbers are there in the set? And we've got 4 numbers in our data set. So just trying to show you an example of doing it by hand. So then you would do this thing, as we said, x minus 10 divided by, yeah, 10 divided by 4. What does that equal roughly?
2.5.
Yeah, good, 2.5. And have I finally got the standard deviation yet, or is there one last thing to do? Yeah, square root it. So when people are doing them by hand in their IA, sometimes they forget to square root. And the last thing is the square root of all of that. Square root of 2.5. It's kind of like saying square root of 2.5 is like the square root of 5 over 2. And you can maybe work that into decimals. It'll tend to give you a decimal answer. You don't know what the square root of 5 over 2 is?
No.
Or square root of 2.5, same thing. Just pointing out you could change it into
1.58.
the 3 sig figs, is it? Yeah. So roughly 1.58. So that's how what the calculator's doing. So what the calculator's doing is it's working out the mean of your data set. It's taking each of your numbers and subtracting the mean. That's what that is. And it's squaring all of those results, because it's squaring it, adding those 4 numbers up, and then dividing it by how many numbers you've got, and then square rooting that answer. So if you did an IA, standard deviation, you had to show the process by hand. You could do it like this, or you could do it, some people do it using spreadsheets. They set up tables in spreadsheets to show they're working out, and so on.
Yeah.
But this is a pretty painful thing to have to do in an exam, isn't it? So you'll tend not to see it so much having to be done by hand in an exam. But we do like to show you just one example in case you do it for an IA. What does the standard deviation tell you again? Does it tell you middle number? Does it tell?
It's like you spread around the mean.
Very good, yeah. It tells you how widely spread the data is around the mean. Whereas the interquartile range and the range told you the spread around the median instead. So good. So this is about the spread around the mean, in case anyone wants to write that down. I'm recording this too, so in case you really don't want to write it down now.
It says on the next page.
What does?
Oh, never mind.
Okay, I'll just move on then. Okay. So what does it all? Oh look, I made a joke. What does
We
it all
don't
mean?
have that. No, that's funny.
I
I
know. I only thought of it after I printed it.
Darn it. That would have been hilarious.
So you, so you can change it if you want.
Missed out on that one.
So that's interesting. So yeah, the standard deviation and the variance. What's it? Oh yeah, how do you get the variance from the standard deviation, by the way?
Variance.
It's, yeah, it's just a standard deviation squared.
Oh.
So
Yeah.
yeah.
Right, yeah.
So it's another way of expressing the spread around the mean. We tend to use standard deviation more to express the spread around the mean, but variance is possible as well. So the larger the standard deviation or variance, sorry. So what does it all mean? The larger the standard deviation, the more widely something.
Spread the data is around the mean.
Yes.
Go mean.
Data is around the mean.
Anybody want to give me some money so I can get a waffle lunch? Miss Melinda, you know how you told me they charge 50 cents for extra chicken? They charged me a whole $2. That's a big difference from what you told me, Miss Melinda.
I'm sorry. Maybe they do. Maybe they charge me $2 too. But you get a lot more, don't you? It's worth it, $2. Like for $2, they put in a ridiculous amount more. Although I haven't had it without the extra for so long, I don't really remember what that was like. Okay, so sorry. Okay, so in general, depending on your different textbooks, they have different numbers for this. So, but in general, like some say about 68% of the data falls within one or two standard deviation of the mean. So meaning, here's your little mean through the center. Let's draw a little mean line going through here. Here's our mean. So about 68% of the data is kind of like falls within the mean.
Does this always happen?
Yeah. Yeah, by definition, yeah.
68%?
Around 68%.
This is definitely
In Australia, we say
65%.
67.
I thought
Oh,
it
does
was
it? Sorry.
67.
Yeah,
Oh,
in
it's
Australia, we say
65.
67.
It says 68% is on the edge of the.
Where did you get 68?
Why would?
Depends on what textbook you look at.
Yeah, I'm confused. Can we just start this page again?
No, it's only I don't understand
How
what
it
this means.
says 68?
Go back to the joke about the meme.
No, but what is it?
Oh, that's a 63 and that's a 68. Oh, in this case, we're saying that the standard deviation must be about kind of like that length. So see, my green line was meant to go through the center. It's meant to be equal. That's meant to be the length of one standard deviation, and that's meant to be the length of one
What are
standard
those yellow
deviation.
numbers?
I think that's the mean plus one standard deviation. The mean minus one standard deviation. I think that's what that was meant
So
to
how
be.
do you know it's 68%?
Oh, it's just a thing that they've decided. The normal distribution people. Gals. Those are gals.
Listen, I'm really confused as to what is going on.
Yeah.
Yeah.
We have to know that.
It's just a formal definition. They say kind of like, 68%, as Lauren said in some textbooks in Australia, they'll say 67%. About 2/3 of the data, roughly 2/3 of the data, has to be within plus or minus one standard deviation of the mean. That's just the thing that they say about the normal distribution. And they also say, in Australia you have to memorize these numbers. 95% of the data, pay attention, 95% of the data is within plus or minus 2 standard deviations. So the mean plus 2 standard deviations and the mean minus 2 standard deviations, that's meant to be almost all of it, 95%. So 95% of the data, like the area under the graph basically, the area under the normal distribution, is meant to be within the mean plus 2 standard deviations. So here's the mean. So the mean plus 2 standard deviations would be that length, and the mean minus 2 standard deviations would take us back to here. So, and then what percent, the mean plus 3 standard deviations and the mean minus 3 standard deviations is meant to be how much of the data?
99.97.
Exactly, like almost 100. It's just a formal thing, and each textbook that you'll see will have slightly different numbers. So as I said, in Australia it's 67 instead, and 95 and 99.5. But they're tiny differences.
You have to know these numbers.
In Australia you do. I've not seen where you need to here. But maybe they want you to sort of like they'll give you multiple choice and you have to pick the most likely one. Yeah, let's do the spots above. So that was a little overview, and now we can then hopefully this will mean the above part makes a bit more sense. Okay, so an example. So if we said the distribution of heights, not Lauren, Owen, you're both in my line of vision. Okay, so the distribution of heights of American women aged...
Are you bullying me today as well?
Yes. The distribution of heights of American women aged 18 to 24 is approximately normally distributed with a mean of 65.5 inches and a standard deviation of 2.5 inches.
So that would be 65.7, 68.
Yeah,
68
something.
that way
Oh.
and then 62 that way.
Yeah, that's where Owen, you should have listened. That's where the 68 and the 63 came from.
Oh, that's for the
Oh, hang
63
on.
and 68. No, but that's 68 and 63%, not inches.
Oh yeah, so here it's saying the mean. The mean is 65.5, yeah, not percent. So the mean is 65.5, and they're saying the standard deviation is 2.5. And we're going to use these numbers to make these calculations. So 68% of the women, heights are between the mean plus 1 standard deviation
Oh,
Oh,
so
the mean one.
68.
and the mean plus. Sorry.
So you just, whatever it is, you just turn that into a percentage, Miss Lily?
Yeah, 68% is the formal definition.
That's
of
what
we're
we're
using for this
happens
question.
numbers are around that right now.
Hmm?
It just so happens the numbers are being left around 16.
Yeah, which is
It's coincidental.
Oh, so it's not really. Oh,
yeah, exactly, yeah. These are the formal numbers that are meant to be the
So
case.
that could be like 12 and like 2.5 or something.
Yeah, these could have been random other numbers. It's just, as Calvin has said, complete coincidence that this number sort of looks like that. That's just a coincidence in this case. So the mean height of the women is 65.5 inches. So 68% have
So
heights
they'll tell
between...
you the standard deviation.
Yeah, you'll need to either calculate it in a previous question or they'll tell you it.
So we just.
Yeah, so either you'll calculate it beforehand or they'll tell you it. So in this case, 68% fall within the mean plus 1 standard deviation or the mean minus 1 standard deviation. So the 63 came from here, the mean minus 1 standard deviation. 65.5 minus 2.5. So if you want 65.5 minus 2.5, yeah, gave us that. 65.5 minus 2.5. And how do we calculate this baby?
Let's add 2.5 to 65.5.
Yeah,
That's right. That's 69.
close?
68.
Where's the 60? Oh, no mind.
Yeah, so that's what's a bit confusing is this number just by coincidence came out to be the same as that.
Well, that's 65.5
minus
Tell you when you said that, I was just ready to get
This one? Are you talking about?
Yellow.
65.5, it's a mean minus 1 standard deviation, yeah. So that's what we just did, the mean minus 1 standard deviation was in yellow. That's how we got the 63. And, oh, and yeah, this is where the 63 and the 68 came from. Interesting. So now they're saying 95% are within plus or minus 2 standard deviations. So what should I fill in this missing spot here?
Mu minus 2 sigma.
Good. Yeah, good symbol use. The mu mean minus 2 standard deviations, the mean plus 2 standard deviations. Or between 60.5, where did I get the 60.5 from?
Somebody, how did you get the thing where it's like the tree stop that? No, I understand.
Answer this. Owen, where did the 60.5 come from? How did I calculate that? Using these blue numbers and the purple stuff.
You put those numbers into
Yeah,
maybe
what?
65.5 minus 2.5.
2 times 2.5.
2 times 2.5, yeah, good. So it's 65.5 minus 2 times 2.5, yeah. Gave us the
Where are we
60.5.
65.5.
Yeah, because we're doing the purple thing and we're subbing in the blue numbers that we're using in the question. And this one, Sarah, how would I calculate this one? What's that one? Yeah. Yeah, good. And anyone want to suggest what that might be?
70.5.
Yeah, good. 70.5. Good. Very good. And we've still got that last one to do as well. I just scroll down a bit. And 99.7% of the data should be between the mean minus 3 standard deviations and...
So wait, the first number 1 relates to the second graph,
Yeah, number 1 relates to the second graph, yeah.
and then number 2 is the third graph.
The third graph, yeah. And number 3 is the fourth graph.
Okay, I'm going to make that a little better.
Yeah, that's a good idea to make a point, make the connection. This question 1 relates to the second graph, 2 relates to the third, and 3 relates to the fourth.
Why are the U things, the mu things, why are they, for number 2, why is it plus 2 thing, and the other one it's a minus 1?
It doesn't matter because it's a range.
Is there a range?
It doesn't
It's
matter.
between 2 things, so it doesn't matter when you put first.
Okay.
Yeah, it doesn't matter which one, whether you say, so it just means from here up to here. So see this one, Isabella? So see from here, this one here would be the mu minus 2 standard deviations, because see the mean minus 2, and this would be the mean plus 2.
Okay.
Yeah, so as Calvina said, it's just meaning between these two points. And this one relates to that one. So 99.7%, almost 100%, but not quite. There's a little bit missing on the sides. Between the mean minus 3 standard deviations, the mean, blah, blah. So, or between, so notice I already gave you the mean plus 3 standard deviations here. So here we need to just fill in the mean minus.
Where did you give it to us?
This one, see I already gave you the mean plus 3 standard deviations. So the one we need here is the mean minus 3
So
standard
it would be
deviations.
65.5. Wait, 65.5 subtract 3 times. 2.5. Yeah. That'll be like 7.5.
Yeah, what does that equal?
58, yeah. 58, man.
58. So see, I don't know if you can see them, there's little yellow numbers down here. This one's saying that that point's at 58, and this one's saying that that one's at 73. So, yeah, in case you want to write those in a bit later. That one, this one down here is probably, I don't know if you can see it well on your printed copies. This one is telling you it's 58 to 73. See, 58 to 73 down here. And the yellow writing down here is saying it's between 60.5 and 70.5. 60.5 and 70.5. And this one down here is saying it's between the other two, 63 and 68. Whereas here I just did a picture of a blank normal
So, like,
distribution.
what is the point of us knowing this?
Just like what is, it's just pointing out like what does the standard deviation mean?
But, like,
Its
why
whole
would you have
purpose
to
is
know
this.
it?
It can, like if you have a big standard deviation relative to your mean, it means the data is really widely spread. But these ones, you would say the data, it's a pretty small, like relative to 65.5, standard deviation of 2.5 is pretty small. So from here you could probably see, because the standard deviation is pretty small, relative to the mean, it's very narrowly spread around the mean, I would say. Whereas as opposed to if it was really widely spread, the normal distribution would be more like that. It's still at the same height, kind of thing, but it would be more widely spread. Kind of like, you know, box and whisker plots. If they're really widely spread, then they're kind of like, you know, like these kind of ones, as opposed to really narrowly spread ones. So if it's a large standard deviation relative to the mean, because if the mean was a tiny number, you probably, I know you've got a tiny standard deviation. It could still be widely spread, but it's all just relative sizes. Like 2.5 is pretty small relative to 65. Yes, Katie.
What about your albino profile?
How do you say it?
C.
Rapido. Alrighty, yeah, so what's the point of it? That's just it. That's really all there is. Can you remember which famous mathematician invented the normal distribution?
Yeah.
Starts with G.
Yeah.
Gauss!
No, wait, I was going to say that just to be funny because you like it.
Do you remember the joke about Gauss and the normal
Gauss
distribution?
in the house.
Yes, there's that. But do you remember the joke about
No.
he invented this? And because in theory, like they're saying that things around in nature and society and stuff just randomly follow these normal distributions. Like human ability, like you know how they curve everyone? They believe that the majority of people are the average. And there's only a few, oh my goodness. And there's only a few people, there's only a few people that would be kind of like low academic ability and a few people that would be really high academic ability. Like the area under the graph's meant to be like the population of people. And in
telling us that Gauss is the bell curve?
yeah, or the joke was that oh, that's right. Gauss didn't discover the normal distribution by studying phenomena in nature and society. That instead nature conformed to his will. Get it? So rather, like he just said to the world, like things will follow this pattern. Like majority of people will be in the middle, and only a few people will kind of be really tall, really short.
Then how is that funny then?
Because this was kind of studied by observing patterns in nature, as if like nature was the dominant force. But still, they're saying he's so strong, he actually just made it up, and the whole of nature and evolution just followed his mathematical idea instead. So, what's that?
Gauss.
Yeah. So rather than say that most people are of average height and a few people are really short, a few people are really tall.
But Chuck Norris
Instead.
but that's not funny.
Yeah, it's not funny.
That's what you should think about.
Nature conformed to his will instead. Yes, you did. Yes, yeah. Okay, all right. Alright, let's try some IB questions. Because he's walking. The age in months at which a child The age, he's walking for the first time and doing it really easily. Okay, Isabella. The age in months at which a child first starts to walk is observed by a group of children. The results are these. What are these meant to be? What is this? Yeah, what does that represent? Age in months that the little kids walked. Find the mean of the ages of these children at their walking height. I mean their walking stage, I guess. So we've got to find the mean, find the standard deviation and the variance. So this is a nice straight up. Grab out your little calculators. What? Yeah, I'll let you guys work it out. So you're going to plug the data into the calculator, and it's going to give you all these answers in one big hit. So, enter data. No, I'm just doing it in case anyone's forgotten. You don't need to write this. You probably remember it.
We only have one line.
Yeah, so make sure all the other lists are clear and that you've just got stat edit and you enter your data into L1. Actually, you go up to the table, like highlight L1 and press clear enter. Don't ever press delete. Just go clear enter. You've got, because it deletes the whole thing. If you do and it's stressing you out, you can just reset your calculator and it just brings it back to life. Then you have to put your diagnostic back on. So enter data into L1. And then what do you press after you've entered it?
That's not the
You should be talking, you should be entering your data.
In order, or do we just put it randomly?
Yeah, no, the data doesn't have to be put in order at all. Yeah. Shh. No.
No,
Yeah.
no,
One bus, that was and it's not a frequency table.
let's go Regression missing out.
Yeah. And I want the mean, and I want the standard deviation. And standard deviation squared is something we'll just have to calculate afterwards. I don't think it gives you the variance. So we're just doing some practice ones. Variance is the standard deviation squared. Just practicing plugging stuff in a calc. Oh, if it says frequency list L2, clear that. Yeah, or else it's going to think there's a or they'll tell you there's an error if you don't have any numbers in L2 either. So yeah, clear. Make sure the frequency list says clear when you do your stat calc. Yes.
It's working, but how are you going to show, and you want us to write that? The working is not this question.
I think the only reason why they have the working space, I guess, is in case anyone just happened to show the mean by hand.
Do we do,
I don't know.
Do we just do 0x?
Oh yeah, or the variance. Yeah, the variance will need a bit of working.
how did you get like the sigma square?
Sigma is just square.
You can do square? Yeah, where's that?
I have for sigma. We just have a sigma x. I've never actually
Oh my god,
2.52 squared.
that's good. That's quite brilliant.
Also, how do I do B? I have no X.
Oh, that's meant to be a mean. Yeah, that's my mistake. That should have been Oh, but they tell you the previous mean. So you could work out what the total would have been, because you know how many numbers there were. So the mean times how many numbers you've got. And then oh yeah, the mean times how many numbers you've got. The old total. And then you can add the two new numbers. Or subtract the two new numbers. Or subtract it to take it. And then divide by 2 less. Okay, yeah, so it's like a little problem solving unit. What did you guys get for your mean?
There's no like thing here that's like the sigma squared. So we have to do it by ourselves.
You can do it by yourself, but also Paige just showed me a way to do it. But yeah, otherwise you would Paige, and I'll have to get it to show me again because I forgot. But for now, what I do is I just write these two down, write them into a few decimal places, and then round it, and then square the unrounded answer.
Cool.
So
3 decimals, that would be 3 sig fig, or just like
3 sig figs, yeah. So it's good to write your dot 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 answer, and then so what would be the dot 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 answer for the mean?
13.7.
Oh, is it exactly 13.7?
13.7. Oh, 7.3.
I didn't get that.
3.
Yeah, and then 13.7. Yeah. So see, doing that's kind of a good idea because you never know, you might need to use the unrounded answer later.
And then it's 2.51837.
So what would that be to 360? Yeah, 2.52. And so what you should do is to get the to get this one, use the unrounded. Use the
Wait,
unrounded.
Miss Melanie?
Huh?
I thought sigma was that little z thing.
It's easy.
You know how that's called sigma?
Oh yeah.
Your adding thing's called sigma too.
Hang on, what am I talking? Did I get that wrong? Yeah. Wait, just 1 second. Let's Google it fast.
Because in math, you learn that you're a big thing called sigma. But then you also learn that you're a circle called sigma.
Maybe this one. Oh, what's that one? What's the other one then? Oh, lowercase. That's interesting. Yeah, of course. Yeah. Uppercase sigma, and they look completely unrelated, don't they? So yeah, uppercase sigma is the E, the funny E, and lowercase sigma is the standard deviation one.
So, when we
I
were
forgot
doing the thing with the mean plus standard deviation, how come you would draw that little thing? This.
That's sigma.
Sigma? Oh, because
Double sigma.
that's lowercase sigma, and lowercase sigma means standard deviation for a population, which is what we tend to use. Whereas uppercase sigma is like the total of, means the sum.
Okay, so lowercase sigma.
Yeah, lowercase sigma in maths is standard deviation. Uppercase sigma in maths means the sum of. They're like, it's as if they're completely different letters. Okay, yeah, so when you're finding the variance, if you're doing it by hand, use the unrounded standard deviation. Don't use the rounded one, you get a different answer. Oh, and what's our answer? 7 point something?
I got 6.34.
For what? For what? I got what?
Did you say 7 point something?
I got
Variance.
6.34.
What did you get, Paige?
Oh yeah, for the rounded version I got.
I got 6.35.
How do we all get different things?
Lauren, what's the answer? Tell us.
I think I got it wrong. I got 32.
Fair enough, yeah. You might have, do you know what you might have done is you might have squared twice.
Yeah,
Because that would make sense, yeah.
I
So
got
2.6.
6.32205649.
So if it's like roughly around the same, is it fine? Because I got 6.34.
Yeah, I got 6.3.
Yeah.
We got 6.3.
You guys see this?
Just make sure you use the unrounded. If you use the rounded answer to square and square the rounded answer, then that's wrong.
You did.
So don't square the rounded answer, square the unrounded.
Yeah,
That's
I
a big
did
deal.
that and I got 6.34.
So if you squared that, Sarah, you got 6.34? Oh, I don't know. See, what's the vote, 6.34?
Yeah.
One of them's gotta be, because like if it was a difference of 1, it's not such a big deal.
No, but you're saying love.
I don't have the calculator. And I'm not sure what happened with that one. Maybe it's just the numbers wrong or something.
Yeah, I still got 6.34.
Okay,
Yeah.
6.34 is good now? So Paige, what do you press to get the, Paige has got another way of doing the variance. And what would you press, Paige? Second stat. Over to math. See number 8. You got standard deviation. You got max, min, median, blah, blah. We'll show you again.
Figuring out the variance in a different way.
Showing you an alternative way. So what would we do again, Paige? Second stat.
Well, I can see a different answer.
Over to math. Yeah. And 8 variance. Second one to tell them L1. And I don't have the data in there. Do you guys want to try that and see if you get the same answer?
I got 7.135.
Maybe it's doing it using the sample instead. The sample standard deviation. Because remember, like there's a population standard deviation and the sample one.
Did it just pick some random numbers from our population example?
Yeah. Oh, because remember, like you know, when you did your data, it gave you S and it gave you sigma. Showing you like what I mean is remember there's 2 different ones the calculator gives you. Back to this stuff. So the calculator gives you 2 types of standard deviations. we use this one, but what it might have done is it might have found the variance using this one. So it might be safer for us to do it by hand then. To just square it by hand is maybe safer. That's the one we use. Do you understand what I mean by S? The S one, first one, sample one was that one. So maybe that's what the calculator's done. I didn't realize that you could do that. Okay, let's do the next little question. Okay, the tree. So I don't know where I got it from. I just googled tree. Owen, you asked about that before.
No, I must dance.
See, it's dancing.
Okay.
Okay, a group. This is a good little.
Is that funny?
I don't understand it.
That's creepy.
Doesn't it look like it's dancing like this?
It's dance and I see it. I see it.
So like, why
Oh,
does
it
that
does.
mean?
It does.
Why is that a
She
mean?
doesn't know. She just Googled tree.
Yeah, and that came up, so I meant that'll do.
Why did
Um.
trees is the most
Because they questioned about tree.
making sure that she was just randomly giving a
Okay, so this is a good problem-solving one. Okay.
Do the median, Miss Delaney.
Did it ask for the median?
13.1. Okay, moving on.
Sorry, did it ask for the median? Where? Oh, sorry, did do.
14.15.
Thank you.
13.1.
Oh gosh, what is it then?
13.1?
13.1?
No.
Yes.
No.
Is it 13.1?
Yeah, I said yes.
Okay. Yeah, let's do that and move on.
It's okay, Grayson.
Sorry.
Oh,
Yeah, I got
Well,
13.1.
oh, I was looking at something else.
Okay, so number 2 is a bit more problem solving. A group of students had measured the heights of 90 trees. That's good to remember, so there were 90 numbers in total. The class calculated the mean height to be 12.4 and the standard deviation to be 5.35. One student notices that the two measurements, 44.5 and 43.2, are much too big and must be wrong. They could be errors. How many standard deviations away from the mean of 12.4 was 44.5?
Let's work it out. So you just subtract it.
Okay, divided by 5.35.
Why do you do that?
Just trying to figure out how many like steps of 5.35 it is away.
Oh.
Yeah.
How
Like how
many?
many big?
How many?
And is that even possible according to the normal distribution?
No.
Yeah, you can only kind of go up like 3 standard deviations and then just a little bit less. And 3 standard deviations that way. So you work out the difference between them, 44.5 minus 12.4. And then, because there were 5.35 deviation. Did you get 6 exactly? Oh, okay. 6. So not possible. For a normal distribution. So that's why they kind of said, no, this is no good. Normal distribution.
Oh, that's a lot.
So we can write in the answer 6 for that one. I'll just leave this here so we can see the question. The incorrect measurements were removed from the data. Calculate the new value. This is meant to be the mean. So let's put a little line above here of the mean.
Not possible for normal distribution.
Yeah, because the normal distribution is just like, not roughly, pretty much the mean plus 3 and the mean minus 3 standard deviations. Then there's a tiny little bit left over on the side. So the mean plus 3 and the mean minus 3 standard deviations.
So our answer is
Yeah, it's still just 6. They didn't ask us to comment on it or anything. It's just an extra thing I put in there. So we just asked to calculate the number 6 is all. Calculate the new mean. So,
Miss Manu, you said it's plus 3 or subtracting standard deviation from the mean.
yeah, generally it's pretty much the mean minus 3 and the mean plus 3 standard deviations. There's a tiny little bit on the side because that's like 99.7, so 0.3% is kind of still here and out here. But it's not really possible for this one to be 6 away from the mean. Oh, okay. Oh, it's messing around. Okay, so B. This is a good problem-solving one. Calculate the new value. So we knew before the mean was 12.4 and the standard deviation was 5.35. So Sarah, if we know the mean was 12.4, and that there were 90 trees, how could we work out what all their heights added up together was? 90 trees, and they've got an average of 12.4 meters.
Sarah answered you.
Oh,
No.
no! Should I say Sarah?
I think she thought she was helping. But was it? Multiplied it, yeah. Exactly. There's 90 trees, and the average came out to be 12.4, so the old total, so old heights total
build heights.
Wait, what's the total? It's 90 trees. Oh, never mind.
Yeah, so you can reword that if you want. I'm just being lazy here. All the tree heights added together would have been 90 times 12.4.
So where did this X come from?
So 1116.
1116.
Oh, the mean. Sorry.
So all the tree heights, yeah. So that was meant to say the mean. It was meant to be have a line on it.
So all tree heights total.
Yeah, old tree heights total, like all of them added together, would have been 1116. So now we're saying that we're removing this one and we're removing that one. So what would be our new height total?
1116.
That minus those two?
With 2 trees removed. Yeah, exactly. Would have been the 1116 minus those two. Yeah. 44.5 minus 43.2. What? Because beforehand all the trees.
Okay, I'm so sorry.
Yeah,
I'm just
that's fine. It is confusing. All of the trees added together, the heights would have been 1116. But now we're deleting these values that we've decided are errors. And so what would be our new total?
1028.3.
1028.3. Do you guys agree?
meters.
Yeah. So that's a new total. So what would be the new mean now? What would we divide by to
You
get the
divide
new
it
mean?
by 88.
88, good, yeah, because we removed 2 trees, those 2 trees. So now there's only 88 in total. So
11.688522.
Great. You guys are about to talk in the city now?
685?
Yeah.
Would you say 11.7 to 360?
Yeah.
I was so moving for it.
What's her name?
And 400.
Stole her shine.
I didn't. She answered it, and then I just said it again.
It's only. Never mind.
So what you would ideally do is write the unrounded answer with a bit of ... and then round it. So if you make an error,
I can see that.
yeah, because then if people make an error in rounding here, maybe the examiner sometimes can just mark the unrounded as correct. But if you didn't have that there, then they couldn't give you anything. And quite often, you never know, later on in a question, they might need the unrounded answer again. So you don't want to have to work it out again. Some more IB practice.
On an IB exam, you just take one like a year after, or are you not allowed to do that?
Yeah, you just pay to take it again. You have to just pay to sit it again. It's really hard to remember it all though.
Yeah.
But yeah, you can retake for sure. But yeah, you have to wait. I think you can wait until November every half year. So if you did the June ones and it just didn't work out for you, you could retake. Like, so I've seen that happen in a school. Once a student couldn't get into his course and he really desperately didn't want to do anything else but that course. So he retook 2 exams that he thought he could do better in.
And he did do that.
I think he did, yeah, he did. And then, but he did them in November because there's a November reset. So he just had to make sure he studied a lot for them. There were things like essays and stuff and like history. He just didn't study enough for his history exam or something, and he was applying for a history course. So he retook, I think, biology and history because he didn't think he could really improve his other scores. So he was happy with them. I can't remember. It was something to do with he was studying history somewhere in the UK. Yeah, so he needed a higher history score and a higher overall score. So that's why he retook biology as well. But yeah, that can happen. You just have to pay for it, and it just means that you have to spend a long time revising. It's amazing what you'll forget in those months in between. It's good.
The water machine next door is really sad, and I compare to them. Can I do that?
Yes. Okay, so we have 2 more.
Practice and do that at home, and just move on to the scatter.
Do you want to?
Yeah.
Okay, yep, sure. So we can leave these ones. Yeah, that's a good idea. I can do that again where we flash up the answers kind of thing. Yep, that's fine. Okay. Oh, out of interest too, I just wanted to guys, it's slowing us down. Oh my goodness. Okay, so standard deviation. I noticed in the topic assignment, there's a few where we talk about standard deviation and its impact if you multiplied all your data set by something, or if you added something to your data set, would it affect the standard deviations? So what do I mean by that? I'll just do a really quick activity to show you. I'm just going to make up some numbers, a really quick data set. Here it is. So quick data set. So let's work out our standard deviation. Stat, edit, one of our, oh, what am I doing? Stat calc, sorry. One of our stats. Make sure my frequency list is empty. I've got L5 in there, so I should change it to L1. Enter.
Yeah, Mr.
What's my standard deviation?
2.23.
Okay, cool. 2.231. Let's just write out the lots.
2.231499.
Yeah, because now it's a little activity where we're going to see what's the impact of multiplying the data set by a number. So I can show you a quick way where we can demonstrate that. So you can see the data set. So if I go back to stat edit, if I don't want to have to multiply each number in my head, I just want to go up to L2 and say equal, or well, it says L2 equals 3 times L1. So trying to see what's the impact of multiplying the numbers, and I'm going to calculate the standard deviation of this one. I'm going to see what's the just a random number. Yeah, trying to see, do we get the same standard deviation if all the data set was multiplied by 3? What if it was divided by something instead? So let's say L1 divide by, what do you want to divide by?
2.
I'll go in between, 5. Compromise. Enter. And then, and now let's see what's the impact of adding and subtracting. So let's say equals L1. Isabella, what would you like us to add?
Times 4.3.
No,
Add. Make sure that is add.
So, plus 4.3.
Plus 4.3. And then now let's just try subtracting something.
Subtract 2.
Subtract 2. Sounds good.
No.
So see, it's just worked out the new data sets for me. Now I'm going to do stat calcs. Oh, and pay attention, please. So now we're going to do, don't answer back, please. So now we're going to do stat calc for each of these and see, do we get the same standard deviation? So try to remember, we were timesing here, we divided by something here, we added here, we subtracted here. So stat calc. So I want to work out what L2 standard deviation is. Do you think it will make the standard deviation if I times everything by 3? What do you think it might do to the standard deviation?
Oh, it'll be 3 6 times 6.6.
Could be. You did? Yep. So timesing all the data, the whole data set, each number in the data set by 3, made the standard deviation multiplied by 3 as well. What about the dividing one? Stat calc again. So this is all in my L3. What? Oh, prediction. So we got 0.44. So it's not the same when you divide each number by something. You get that number divided by, what did we divide by? 5, wasn't it? So this number, the standard deviation was divided by 5 when we divided the whole data set by 5. What do you predict adding or subtracting might do?
Add, subtract away from
Yeah, miss?
No.
Because remember, standard deviation is about how widely spread around the mean is it? Matthew? Okay, yep. So how widely spread around the mean? This is L4, isn't it? So if we added numbers to everything, does it make the data more widely or narrowly spread around the mean? It's the same, yep. So would you agree, the mean just moved up a bit. If you add a number, the means become slightly higher on the number line, but the spread around the mean is still the same. Because standard...
If you subtract.
Yeah, because the mean changed, obviously, but the standard deviation, and the same if you subtract. So that was just... yep, sure thing. That was just because in your topic assignment, there's some questions like that. Yep. All right. Okay, so moving on to scatter graphs. Let's do a quick intro to scatter graphs. Reg and Pearson's. This is the TA2 stuff. TA2. Okay, scatter graphs, linear regression, and Pearson's correlation coefficient. We're flying through this a bit. Is the trend on this scatter graph linear or not linear?
Wait, Miss Maloney, just like the last question, how do you find the standard deviation of variance? The one that we skipped.
The one we skipped? This
I'm
one?
just confused.
Yeah, good point. So you'll need the midpoint. Oh, no, actually, there is no midpoint. It's just X list will be 0, 1, 2, 3, 4.
Oh, so you just put it in the calc.
And the frequencies would be in L2 because it's a think of this
right,
as a
okay.
frequency table, yeah. So you could turn this into a frequency table And then you just do it all again, but using a frequency table. I just wanted one example where it was a frequency table
okay.
instead of a single list. And then after that, it's the same. So yeah, is this linear?
Yes.
Yes.
Yeah, it's kind of a straight line. Is this one linear?
No.
No, it's kind of a bit more either logarithmic or quadratic or something like that. Is the correlation moderate, strong, weak? Is it positive, negative? Do you remember things like this from year 7 probably? Year 7? Remember doing these little things? Weak just means it's more scattered. Strong means it's pretty close to being a line. Moderate is kind of in between. If it's no correlation, what would it look like? Yeah, completely random array. So from your textbook has got a definition of what might be considered weak, moderate, and strong. Your textbook, each textbook says something completely different. Your textbook says strong is where you've got your values between roughly 0.75 and 1. So something like negative 0.8 would be strong negative. Something like positive 0.78 would be strong positive. Moderate, they're saying, is between 0.5 and 0.75. Oh, okay, weak would be between 0.25 and 0.5. I'm so sorry. You were. You just look like you're falling asleep. Okay, 0.25 and 0.5. Sorry, Darwin. You probably were. 0 to 0.25 is very weak. 0 is like no correlation. So as I said, different textbooks, different publishers might have a completely different table. You tend not to be expected to memorize these exact boundaries, but they might give you more obvious answers. They might give you something like 0.89 or 0.91, and they expect you to realize, yep, that's clearly got to be strong, positive. And moderate, they'll give you something pretty clearly moderate, like 0.6 or something like that. Weak, they might give you something like 0.3. Okay, Lin regs and Pearson's on the calculator. Linear regression means just finding the equation of the line of best fit, like y equals mx plus c. Scatter graphs are drawn so that the x-axis is a something variable and the y-axis is the good, yeah, independent. Independent on the x axis. A bit like science, isn't it? Yeah, that's the same thing, that the independent variable of the y. Independent. The dependent is affected by a change in the independent variable, supposedly. If you draw a line of best fit on your scatter graph, you should make sure it passes through the something point. Remember those things from CAE? No. Mean point? Do you remember, like you'd have a scatter graph and it'd ask you to find the mean of x and the mean of y, and you'd have to plot that point, and your line of best fit would have to go through that mean point in CAE. So, like, imagine you had your scatter graph. And then you found the mean of x and the mean of y, and you plotted that little point. Your line of best fit has to go through it, or else they say that you did it wrong.
How do you
find the mean point? Yeah. So sometimes they'll tell you the mean point, but quite often they'll get you to calculate the mean point, which is the mean of x and the mean of y. Okay, passes through the mean point and make sure, okay, yeah, so when drawing a line of best fit, make sure that it passes through the mean point and that the y-intercept matches the one found from your
Linear regression.
Good, yeah, linear regression.
What's a linear regression?
It's when you find the line of best fit. Like, you know, line of best fits are like y equals mx plus c, straight lines. So just make sure that it passes through the mean point. And if you've been asked to find a linear regression, that the y-intercept's the same as the c value that you've got. Because like y equals mx plus c. Just make sure that your y-intercept is the same as the c value that you got from linear regression. Two things. And that it kind of looks like it follows a trend. Like you can't do one that's like out here, that would just be wrong. To do a linear regression, you find the values and find the value of Pearson's R. You do this, you do stat edit, which just seems to be where we always go. Enter the data in L1, independent variable in L1 and the dependent variable in L2, X then Y. Stat calc linreg. So instead of stat calc 1 var stats, you're doing stat calc linreg. Your X list should say L1 because that's the independent variable, and your Y list should say L2. Your frequency list should be empty. That's important. Like, I don't think I see any ones where they put them in frequency tables for you. in our course for these ones. So the frequency list should be empty. That's easy to miss. Then suddenly up will pop up, y equals ax plus b. You can see it gives you in the form of ax plus b. Which one of these two is your y-intercept?
B.
B, good. And which one is the gradient?
A.
Yeah. So I tend to write it out, the ... answer for each one, and then when I do my linreg, I do 3 sig figs. But it's good to write out the ... answer, like a equals the dot, like 5.4327, blah, blah.
So what's the A value here?
In this case, that's like, think of that as mx plus c, but the calculator instead says ax plus b. That's all.
So what's 5.43?
Uh,
Just an example.
An example, yep. How you would write the final answer. Some people write out what a is, they write out what b is, but they forget to put it in the equation.
So that's the equation for the line of best fit.
Yeah, good. Exactly. Because lines of best fit are y equals mx plus c. But in our calculator, they say y equals ax plus b. Just because that's the way the TI-84 expresses it. So our c is our y-intercept, negative 7.21, and 5.43 is our gradient, rounded to 3 sig figs. Oh, and it says your gradient a and y-intercept b should be displayed. Make sure to round these to 3 significant figures. It is long. But yeah, putting the ... answer is probably a good idea to begin with for your a and your b. And then write your equation like I did in blue. Like make sure you do that step, because sometimes people forget that last, putting it in the equation thing. If the value of Pearson's correlation coefficient isn't displayed, when you do a linreg, the R value should pop up. And if it doesn't, that's because your stat diagnostic was not on. So to put your stat diagnostic on, you go mode, go down to the bottom, scroll to the bottom and check stat diagnostic is on.
Is that already if it's on for everything?
Yeah, you'd keep it on forever. But when the calculator's reset or when you first buy it, it's automatically off. So you have to at some point switch it on.
Do you ever use radians in this ID course?
Yeah, sometimes we do use radians, yeah.
Were we gonna learn about like circles and radians and how,
Unit
like,
circles and
360
conversions.
equals,
Yep.
I don't like
Totally.
that.
So yeah, whereas in math studies it's just in degrees, whereas in our course we have to do degrees and radians. Radians we do it quite a lot actually.
Es el tiempo para ir.
Is it time to finish? Okay, so that's how you do a linreg. This stuff is the TA2. So bring your TAs. Feel free to stay around and ask questions too if you have questions about the TA.
Are we working on a topic assignment next lesson?
Yeah. Probably not the whole of next lesson. We'll probably quickly finish this.
Asking questions.
You sure? Okay.